In the last section of chapter 1, we're going to take a look at the normal distribution. Now, we're going to just be introducing it here in section 4. We'll talk about it again and in much more detail in chapter 5. So to start off, we're going to review percentiles. So Julia receives a score report detailing her performance on a statewide test. On the math section, Julia earned a raw score of 39, which placed her in the 68th percentile. This means A, Julia did better than 39% of the students who took the test. B, Julia did worse than about 39% of the students who took the test. C, Julia did better than about 68% of the students who took the test. D, Julia did worse than about 68% of the students who took the test. Or E, Julia got fewer than half of the questions correct on this test. So if you remember from last section, when we were talking about percentiles tell you what percent of the data is below that. So if she got a 39, which placed her in the 68th percentile, it means 68% of students did worse than her. So that means that it's C. Julia did better than about 68% of students who took the test. So that introduces us to standardizing, which many of you have probably seen before on past state tests that you have taken. So Mallory took a physics test and got an 86%. Did she do well? For many students, the answer to this question depends on how well the rest of the class did. So in general, 86% is not considered a bad score. It's a solid B, but it is dependent on how well the rest of the class did. So we're going to look at two different means. So if the class mean was 97%, did she do well? And the answer to that would be no, because it would show that she scored below everyone else. If the class mean was 62%, did she do well and why? So this time it would be yes, because she scored above everyone else. So percentages are all relative based on what the mean was. So in fact, we use standardizing to calculate how far away an observation is from its mean. So standardizing takes a look at how many standard deviations above or below the mean an observation falls, and that lets you know how well you did in relation to everyone else. So on this physics test, Mallory scored an 86%. On the next test, she scored an 82%, which was a more impressive score. So you can't just compare an 86 and an 82 and say, well, an 86 is better, because we have to look at the mean. So how well Mallory did relative to the class. We need to know how well the class did. So on her first test, Mallory scored an 86 and the mean was an 83. And the standard deviation was 4.5%, which means on average, the percentages were around 4.5% above or below the mean. On the second test, Mallory scored an 82%, the class mean was a 78, and the standard deviation was 5.2%. So again, 5.2% above or below the mean was about the distance. So subtracting her scores from each of the means tells us the distance from the mean. But to determine if that distance is a typical distance, we divide by the standard deviation to see how many standard deviations it is away from the mean. So the number we get, how many standard deviations away from the mean an observation is called a z-score. So if we were to compare Mallory's two tests, all right, so for the first test, her z-score, which we always abbreviate with a z, we're going to take her test percentage, we're going to subtract the mean, and we're going to divide by the standard deviation. So her percentage was an 86, the mean was an 83, and the standard deviation was 4.5. So 86 minus 83 is 3, divided by 4.5, which gives us 0.67. For the second test, we do the exact same thing. We take her test percentage, 82, we subtract the mean, 78, and we divide by the standard deviation, 5.2. 82 minus 78 is 4, divided by 5.2 is 0.77. So the higher your z-score, the more standard deviations you were from the mean. So that tells us that Mallory's score on the first test is going to be better, and we're going to talk about it in more detail. So when we're interpreting this, a z-score of 0.67, which is from the first test, means that Mallory scored 0.67 standard deviations above the mean. And for the second test, a z-score of 7.77 means that Mallory scored 0.77 standard deviations above the mean. So, technically speaking, I misspoke previously. She did do better on the second test relative to the rest of her class. So she has a z-score farther above the mean than 0.67. So if X is an observation from a distribution that has a known mean and standard deviation, the formula for z-score is z equals X bar represents our mean minus, sorry about that, wrong direction, X minus the X bar for our mean, divided by the standard deviation, or, and this is something we're going to talk about in more detail about the mathematical symbols for mean and standard deviation, X minus mu all over sigma. Now, these are more related to population mean and standard deviation than they are sample. So we'll talk about these more later on in the notes, but we'll also talk about them more when we get into chapter 5. So just a couple things to review about z-score. It tells us how many standard deviations from the mean an observation falls and in what direction. So observations larger than the mean have positive z-scores. Observations smaller than the mean would have negative z-scores. So you can have positive and negative z-scores. So for example, Francisco took 3 standardized tests. He scores 600 on all 3. Using z-scores, rank his performance on the 3 tests from best to worst if the means and standard deviations for the test are as follows. So for test 1, the mean was 500 with a standard deviation of 80. Test 2 had a mean of 470 with a standard deviation of 120. And test 3 had a mean of 560 and a standard deviation of 30. So my z-score for test 1, so if we're distinguishing between multiple samples, we usually indicate it with a subscript. So for test 1, I'm going to put z sub 1. We know his score is 600 minus the mean 500 over our standard deviation 80. Gives us 100 over 80, which is a z-score of 1.25. For the second test, 600 minus the mean 470 all over the standard deviation of 120. 600 minus 470 is 130 divided by 120 is 1.08. And lastly, for the third test, 600 minus 560 over 30. 600 minus 560 is 40 over 30, which is 1.33. So remember, the higher the positive standard deviation, the better your score is, because it means you're farther above the mean. So this tells me that test 3 is best. The first test would be his second best. And then the last test is technically his worst test. So that would be D, 3, 1, 2. So just because 600 is farther away from 470, you would think that that's the test Francisco does the best on. It also has the largest standard deviation, which means it's the test that most people had a lot more spread in the data. Whereas with test 3, he got a 600, which is only 40 points better, but the standard deviation was so small, there wasn't a lot of spread in it, which means a lot more people were closer to the mean, which means a 600, which is above it, is a lot better of a score. So along with z-scores come density curves. So what we do is we take histograms and we can make density curves that go along with the histograms, kind of like what we did in section 3. So we have a histogram of student scores, test scores. If the distribution is symmetric with no outliers and a smooth curve has been drawn through the tops of all of the bins, kind of like what we did in the last section, this curve is called a density curve. And again, we'll go into a lot more detail on these in chapter 5. So density curves, like distributions, come in many shapes. It's often a good description of an overall overall pattern of a distribution. And we do prefer symmetric density curves as well. So outliers, which are departures from the overall pattern, are not described by the curve. And the total area under the curve is 1. Or if you're looking in terms of percentage, it's 100%, because all of the data under the curve everything under the curve represents all of the data, which if you convert to percentages, because that's what we're going to be looking at a lot here, should add up to 1. So a density curve is always on or above the horizontal axis, so it can never have negative values. And no set of real data is exactly described by a density curve. It's an approximation that is easy and accurate enough for practical use. So the median of a density curve is the equal areas point, which is just another way to say where the median cuts the area of the curve in half. And the mean of the density curve is the balance point of a distribution. So it's easier to explain that with a graph. So the density curve, if you think of it as a weight, the mean is the balance point on this scale. So you have even weights on each side. So let's take a look at a few examples. So if we were looking at a skewed right example, all right, so if you remember back to section 3, if we are skewed right, it means that most of our data is at the lower end. All right, so when that happens, the median tends to be at the lower end, but the mean tends to be a little bit higher because there's some values at the higher end that pull that mean up. If you're looking at a left skewed graph, where most of your data is the right end, your median tends to be higher than the mean to kind of balance it out. And then you have a distribution where it's symmetric and the median and the mean end up being equal. So when we're looking at density curves, they're idealized description of the data. So there's a difference between mean and standard deviation of the density curve and then also a sample. So if we're looking at sample mean, which is what we have been discussing previously, we always use X bar. And if we're looking at the sample standard deviation, we've been using S sub X, or we can sometimes just use an S. If we're going to use subscripts, it's usually if we're looking at two different sets of data and we have two different sample standard deviations we're going to look at. Whereas the mean of the density curve, we use a lowercase mu, which is a Greek symbol. The standard deviation of the density curve is a lowercase sigma, which is also a Greek symbol. So with density curves, we can roughly locate the mean based on its shape, but there's no easy way to locate standard deviation in general. So the important type of a density curve is what we call a normal curve. So these distributions are that they describe are called the standard normal distribution. So characteristics, they have the same shape. They're symmetric, single peaked, which means they're unimodal, and they're bell-shaped. So they're kind of like the perfect distribution, if you will. Any normal curve is described by giving the mean and standard deviation at typically they abbreviate with it a capital N, and then the mean and standard deviation in parentheses. I'm not going to use this notation a lot, but you may see it on occasion. And the mean is located at the center. So the mean and the median in a normal distribution are the same, and the standard deviation controls the spread. So there is a rule with a normal distribution called the 68-95-99.7 rule. And it's a mathematical statement that tells us that approximately 68% of observations fall within one standard deviation of the mean, 95% of the observations fall within two standard deviations of the mean, and approximately 99.7% of observations fall within three standard deviations of the mean. And this is true for any distribution. It's not specific to one type of distribution. It's actually a pretty interesting fact. So, for example, if we looked at a nice symmetric curve, our mean is going to fall in the middle. And when we travel 1, 2, and 3 standard deviations in both directions, that's what contains our percent of data. So we can go in the positive direction, our number of standard deviations, and we can go in the negative direction. So we're always talking about the middle 68%, the middle 95%, and the middle 99.7% when we're talking about this rule. It's always in the middle. It's from the mean going in either direction. So you're always splitting it in half. So if the middle 68% is one standard deviation, that's one standard deviation above and below. So that means 34% is on either half. Then if you move 2 standard deviations, that's when you get the 95%. So 95% divided by 2 is 47.5. And we've already accounted for 34% of it. So that leaves us with another 13.5%. Okay. And then we have 3 standard deviations, which is 99.7, which if you divide by 2 is 49.85 above and below, but we've accounted for 34 and 13.5%. So that's going to give us 2.35% in our next. All right, now we add all of this up, and obviously we're only accounting for 99.7% of data. So the remaining 0.3 is outside of that, which is split up. So the remaining 0.15% of data is more than 3 standard deviations above or below the mean. So let's take a look at an example. So the distribution of heights of young women aged 18 to 24 is approximately normal. with a mean of 64.5 and a standard deviation of 2.5. So this is in inches. It doesn't distinguish it here, but we are talking about in inches. So we are going to sketch a normal density curve for our distribution, and we're going to label the points 1, 2, and 3 standard deviations from the mean. So we're going to start by drawing our curve, and then our mean is the 64.5, which is in the middle. Okay. Then we're going to go 68%. So 1 standard deviation above is, so a standard deviation is 2.5 inches, so I'm going to go 1 standard deviation above. So that gives me 67, and I'm going to go 1 standard deviation above, which is 62. Then I'm going to go up 2 standard deviations and below 2 standard deviations, and this will be 95%. So another 2.5 inches, so that's 68.5, and then 59.5, and then I'm going to go my 3 standard deviations, which is 99.7%. So another 2.5 inches, that gets me to 72 and 57. So it tells me that 99.7% of young women aged 18 to 24 should be between 57 and 72 inches tall. So we can also use normal distributions to find percentages. So what percent of young women have heights greater than 67 inches? And we want to show our work. Well, we know that 67 inches is 1 standard deviation, which is 34%. If you think back to our previous graph where we split it up. So everything above is 50% minus the 34% between the 64.5 and the 67, because we're looking for strictly greater than 67. So that 34% leaves us with 16%. Now there is another way I could have done this. I could have used the percentages above 67, which we knew were 13.5, 2.35, and 0.15 from before, and add it up. But it's easier just to do as little calculation as possible. So next we want to know what percent of young women have heights between 62 and 72% inches. So you have, now we can't just say it's 68 because we're between 62 and 65. We have to take everything that's above 62 inches, which represents 84% of our data. If we take the 62 to 67, which is the 68%, plus the additional, or just 100 minus 34, because we know that what's below 62, minus the amount that's above 67, which from the previous page we know that anything above the 99.7 is 0.15. So I'm doing 84% minus 0.15%, which is 83.85%. So we can also see a big portion of women are between 62 and 72 inches tall. So what if we wanted to look at a percentage that wasn't indicated by 1, 2, or 3 standard deviations exactly? Suppose we wanted to look at the percentage of young women who have a height greater than 70 inches. So our rule doesn't help us with that, which is where the z-score formula comes back into play. So what we're going to do is standardize each of the points we made on our density curve and draw a new density curve plotting the standardized values. So the lowest point was 57. So I'm going to do 57 minus my mean, 64.5, all over my standard deviation, 2.5. And once I do that, I'm going to get negative 3. My next value, 59.5, I'm going to subtract 64.5, then divide by 2.5, and I'm going to get negative 2. Then I'm going to take 62 minus 64.5 divided by 2.5, and I'm going to get negative 1. If I kept going, so I get to my mean, 64.5 minus 64.5 all over 2.5, it's obviously going to result in 0. So if we look, our number of standard deviations results in a standardized score of 1, 2, or 3, depending on how many standard deviations we are. So if I redrew it, my mean would be 0, then I'd have standardized scores of 1, 2, and 3, and then negative 1, negative 2, and negative 3. It's the exact same thing, but I've now standardized it. So what we've just drawn is what's called the standard normal curve, which is the normal distribution with a mean of 0. So our mean is now 0, and our standard deviation is exactly 1. So if we standardize any set of data, we get this curve. Because if we're looking at 1, 2, or 3 standard deviations above or below our mean, it doesn't matter what the numbers are or what the standard deviations are, they're going to result in z-scores of 0, 1, 2, or 3. So this helps us because it means we can find proportions of data values located on any interval we want, not just the 68, 95, 99.7 intervals, which deal with percentages. Now, we're not always going to standardize curves that are going to give us nice exact values that are going to be where it's going to be easy to find the percents that are above or below that. So we can use a table or we can use our calculator. So the table you're going to have access to in Canvas. So what it is an area, is a table of areas under the standard normal curve where the value for each z is the area under the curve to the left, which is a really important distinction to make. We can also use our calculator. And if you hit second vars, vars is right above tangent on your calculator, and then you want to go to normal 2, which is normal CDF. It means normal cumulative density function, and cumulative density function is from section 3 as well. The lower bound can be a data value or a z-score, same with the upper bound. And for our mean, we can use the mean of the data or 0 if we're dealing with z-scores. And for the standard deviation, we can use the standard deviation of the data or 1 if we're using z-scores. So we're going to take a look at some examples. So if we want to find the area under the standard normal curve to the left of a z-score of 1.15, the proportion of observations from the standard normal curve that are less than 1.15, the probability of randomly selecting an individual from a normal population whose z-score is 1.15 or less, or the percent of z-scores that are less than or equal to 1.15, they all ask the same thing, more or less, and they give the exact same answer. Now, with something like this, less than and less than or equal to are considered the same thing. Same thing with greater than or equal to. We assume that they result in the same. So let's take a look at some example. We want to know what proportion of values lies under a z-score of negative 1.25. So there are 4 different words you might see here. Proportion, area, probability, or percent. Now anything that is an area a proportion or a probability is always written as a decimal. Percent is the only one that will convert to a percent because percent does mean percent. So it does indicate whether or not you're leaving it as a decimal or writing it as a percentage. So if I were to draw my curve, okay, because we're given a z-score, we have a mean of 0. If I were to label negative 1.25 is roughly here. So I'm looking for the area that lies under it. So everything to the left. So if you want, you can use the table. You can find where negative 1 falls on the left. Then you go over to 0.25, you find where they cross-reference. But I find that it can be pretty difficult. You can lose your place. So I like to use the calculator. So you're going to go to normal CDF. Your lower bound is negative 1e99. So this represents negative infinity because I can't actually type in the smallest negative number to say that I want something less than that. We use this notation to represent negative infinity. My upper bound is my negative 1.25 because that's as high as I want to go. My mean is 0 and my standard deviation is 1. And then I put enter into my calculator and we're going to get 0.1056. And if I use the table, I get the exact same decimal. Now we want to look at the proportion of values that lie above 1.25. So again, we have 0. We have our standard normal curve, positive 1.25, and the area above is to the right. Now, this is where it gets a little bit more difficult with the table because the table is always area below. So if you were going to use the table, you would have to go to positive 1.25, find where it crosses, and that would be the area below. You would then have to subtract it from 1 to get the area above. Or we can use the calculator. So for the calculator, we have normal CDF. Now this time my lower bound is 1.25 because I'm looking at above. My upper bound is positive 1e99, which would represent positive infinity. My mean is 0, my standard deviation is 1. And when I hit enter, I'm also going to get 0.1056, which is what I would have gotten if I'd used the table and subtracted. So if I'm looking at a value and I'm looking for the proportion that's below that number or the proportion that's above the positive, I'm going to get the same. Because they're at the same location, just one of them is below the mean and the other is above the mean. So the area below it and the area above it is going to match. Next, we're going to look at between. So I want to know what proportion of values lie between a z-score of negative 1.64 and 2.33. So again, if I'm looking at my curve, negative 1.64 is below, 2.33 is above, and I'm looking for the area in between. So if you wanted to use the table here, you would have to find 2.33, get its decimal, negative 1.64, and then you would subtract them. You can also use normal CDF, where the lower bound is the negative z-score, negative 1.64. The lower bound always has to be the smaller number. The upper bound is 2.33 with a mean of 0 and a standard deviation of 1. You hit enter and you're going to get 0.9396. Now notice how I've been going 4 decimal places here and not the regular 2, and that's because with the z-scores and normal curves, we want to be as accurate as possible. So if I go 4 decimals, if I'm asking for percents or proportions, it's going to be more accurate than if I just go 2 decimals. Because if you are looking at the table, a lot of the z-scores have the same probability to 2 decimal places. So we want to be more accurate, so we go 4 decimal places so that we are distinguishing between the different z-scores. Last example is find the proportion of values that lie above 1.34 and below negative 2.78. So this is a little bit different because we're not going to be between 2 values. We're going to be outside 2 values. So we have our mean, we have 1.34, and I'm looking to be above that. And then we have negative 2.33, and I'm looking to be below that value. So I'm looking to be outside. So again, 2 ways to do this. So if I'm going to use the table, it's going to be a lot more steps. So I'd find 1.34. I'd take that decimal, I'd do 1 minus it to get the proportion of values above 1.34. I'd use the decimal from the table for negative 2.33, and then I'd subtract them. If you're going to do normal CDF, the easiest way to do it with normal CDF is find the area in between the 2 and then subtract from 1, because the area in between makes up the rest of the data. So my lower bound is going to be negative 2.33, sorry, 2.78. Miswrote it. Negative 2.78. My upper bound will be 1.34. My mean is 0. My standard deviation is 1. So when I plug this into the calculator and I hit enter, I'm going to get out 0.9072, which is the area in the middle here. But I want the area outside of that, so we're going to do 1 minus 0.9072, which is going to result in 0.0928. So very little of the proportion of values lie above 1.34 and below negative 2.78. So when we're just looking at z-scores, it's kind of hard to understand what we're talking about because we're just looking at, okay, these are z-scores. We're going to be looking a lot more with word problems and how it relates to that. So on a typical Saturday, Fiesta Market reports that the mean amount of money spent by customers is $27.21 with a standard deviation of $7.93. The distribution is roughly normal. So we want to know the middle 95% of customers spent between what 2 amounts? Well, we know 95% is 2 standard deviations. So what I can do is take my mean, 27.21. I can add 2 standard deviations, so 2 times 793, and I can subtract 2 standard deviations to get my interval. So 27.21 plus 2 times 793 is 4307. 27.21 minus 2 times 793 is 1135. So we can say between $11.35 and $43.07. So when we have word problems with units, we do want to make sure that if we find an actual value and not a proportion or an area or a percentage, that we're remembering the units. Okay. So if a person spends $10, in what percentile does that place her? So what we want to do is find our z-score, because $10 is not an exact number of standard deviations to figure out what percentile we're in. So we're going to take 10 minus 27.21 divided by 793. And we're going to get negative 2.17. Now, we have a choice here. We can use the table or we can use normal CDF. And here's what I'll tell you if we aren't given a z-score beforehand and we have to calculate it ourselves. If you have to round your z-score at any point in calculating it, like we had to do here, I would not use the table because it's not as accurate. Because I've already rounded once, I can go straight to the table. There's also, like, because my z-score isn't exact here, it would probably be best if I had just used normal CDF with my exact values, but that doesn't show work, so we're not sure how we got there. So it would be best to just use normal CDF here with our exact values, but we're gonna go ahead and show it with the z-score. So you can use your table, negative 2.17, find it on there, get your area. We can also use normal CDF. So once I standardized it, my mean is 0, negative 2.17, and because I want to know what percentile I'm in, percentile is always area below. So my lower bound would be my negative 1 E99. My upper bound would be negative 2.17. My mean is 0, my standard deviation of 1. And when I hit enter, I should get 0.015. Okay. So now that's the probability. I want to convert it to a percentile, so I multiply it by 100, which puts me in the 1.5th percentile. 1.5 percentile. So not a very good percentile. It means that not a lot of people spend $10 or even less at this market. Now, we can also say if I spend $40, what percentile am I in? So, again, calculating our z-score, 40 minus 2721 over 7.93, it's going to give us 1.61. Now, this does say top percentile. So in this case, when I'm looking at 1.61, I'm looking at the area above because I want to be in the top. So this is again saying we can use the table, find 1.61, take the decimal we get, and subtract 1.61, subtract it from 1. Or we could use normal CDF. Our lower bound is 1.61. Our upper bound, our upper bound is going to be the 1E99. Mean of 0, standard deviation of 1. And we're going to get 0.0537. So if we convert that to a decimal, that's the top 5.37% of spending. So she's in the top 5% of spending roughly, which means 95, roughly, little bit below 95% spend less than her. Okay. Next, we want to figure out is how many people spend between $20 and $30. So I'm going to have to calculate two z-scores here. So the z-score for my lower bound is going to be 20 minus 2721 over my standard deviation of 7.93, which gives me negative 9.91. My second z-score will be 30 minus 2721 over 7.93, which gives me positive 0.25. So mean of 0, negative 0.91, positive 0.35, not very high z-scores. We're looking in between those. So my lower bound is negative 0.91. My upper bound is 0.35. And then my mean is 0, my standard deviation is 1. And that is going to give us 0.4554. And it just say how many people spend. It should say what proportion of people spend. I'm not going to find the number of people. I'm just going to leave it as a proportion. So roughly 45%, so a proportion of 0.4554. So in the examples we just did, we were given information, we calculated the z-score to find a proportion. We can also work backwards. So if you know a proportion of data falls below, above, or in between, you can work backwards to find the associated z-score or the data associated with it. And we'll typically do this by using our z-score formula. So we know that we are negative 2.3 standard deviations below the mean. So we have a z-score of negative 2.3, a mean of 23, and a standard deviation of 5. We want to know what the x value is. Just to refresh, the z-score formula is x minus x bar all over our standard deviation. So I know 3 out of those 4. I have negative 2.3 equals x minus 23 all over 5. So remember how to solve equations. First, I'm going to multiply both sides by 5. I'm going to get negative 11.5 equals x minus 23. And then I'm going to add 23 to both sides. And I'm going to get positive 11.5. These make more sense if you have a situation so you know what x actually means. So same deal. Z is 1.45. We have a mean of 105, a standard deviation of 1.34. We want to find our x value. So 1.45 equals x minus 105 all over 1.34. So we're going to multiply by 1.34. We're going to get 1.943 equals x minus 105. Then we're going to add 105. And we're going to get x equals 106.943. We can also be given a proportion to find the z-score. Okay, so we can work backwards using the table, or we can use our calculator. So this time, if you go to second bars and scroll down to number 3, INV norm, all you have to do is plug in the percent to the left as a decimal. So it's a lot easier to use INV norm to find your z-score than it is to use the table. So if we have 20% of the data lying below a particular z-score, what is that z-score? So we have 20% is below the z-score. So we don't know what the z-score is, but we know the area below is 0.2. We don't know what the z-score is. So we go into INV norm. I'm going to put in my area, 0.2. My mean is going to be 0, and my standard deviation is going to be 1. And I'm going to hit enter. And I'm going to get z equals negative 0.84. If I wanted to use my table, I would find the decimal 0.2000 and find the z-score that is closest to it. You might end up being about 100th off in some cases, but you'll get pretty darn close. Sometimes they aren't going to be exact, which is why INV norm is a better approximation. If you have 34.5% of your data lying above a z-score, what is that z-score? So we have our mean. We have 0.345 is the percent above. So remember, INV norm deals with percent below. So if 35.5% is above, the amount below is 64.5, so 0.645. So when I use INV norm, my area below has to be 0.645. My mean is 0, my standard deviation is 1. It's going to be a z-score of 0.37. Sorry, I typed my decimal wrong. This should be 655. So it should be 0.3. It would be 0.39885, so I'm just going to put 0.399. This is one of the few cases where I'm going to go 3 decimal places because it's not exactly 0.4. It's close enough, but it's not exact, so I want to leave it as 0.399. Next one, it says, if you have 35% of the data lying symmetrically in the middle of your distribution, what are your z-scores? So this is a case where I'm given a middle percent of data, which means there are going to be 2 z-scores. So we know that in the middle, we have 35%. So I need to figure out what percent lies above and what percent lies below. So I'm going to do 1 minus 0.35, and then I'm going to divide by 2. Because it's in the middle, the same percent lies above as it does below. So that's going to be 0.325. Now, I only have to do INV norm once. And I'm going to do INV norm with the lower, with my area of 0.325. And my mean of 0 and my standard deviation of 1. Because if we remember, if you have the same amount area above and below, you have the same z-score, just one positive, one negative. So if I use the area below, I get a z-score of negative 0.45, which my second z-score means that it is positive 0.45. So let's put it all together. On the most recent test, a student scored in the 40th percentile. The mean of the test scores was an 85, and the standard deviation is 1.5. What was the student's score? So the first thing I have to do is use the percentile to find the z-score. So I have my mean. I know that my z results in being in the 40th percentile, which means 40% scored below. So I'm going to use INV norm to get my z-score. My area is going to be 0.4. My mean will be 0, my standard deviation will be 1, and it gives me negative 0.25. Now I'm going to use my z-score formula to find my student's score. So I have negative 0.25 equals x minus 85 over 1.5. So multiply both sides by 1.5. And that gives me negative 0.375 equals x minus 85, then add 85. And that tells me that the student scored an 84.625. So on another test, a student only had 10% of their classmates score better than them on the test. The mean of the test scores was a 76 and the standard deviation was 2.2. What was the student's score? So in this case, we know that our z-score resulted in the area above being 10%, which means to find my z-score, I need to put in the area below, which ends up being 0.90. So 0.9, my mean is 0, my standard deviation of 1, results in a z-score of 1.28. So if 1.28 equals x minus 76 all over 2.2. So we're going to multiply both sides by 2.2. We're going to get 2.816 equals x minus 76. Then add 76. And the score was a 78.816. Now, sometimes it's not always going to make sense for our final x to be a decimal. Because, for instance, we could be finding number of people. We could be finding, so anytime we're talking about anything that's living, like a person or an animal, it's not going to make sense for us to have a decimal answer. But in this case, you can technically get a decimal score on a test, so it's fine for us to leave them as decimals. Last two examples. So an athletic association wants to sponsor a foot race. The average time it takes to run the course is 58.6 minutes with a standard deviation of 4.3 minutes. If the association decides to award certificates to the fastest 20% of the racers, what should the cutoff time be? Now, problems that contain time can be a little bit tricky because you have to think about it a little bit. Because if I want to be in the top 20% of the racers, that means I want to get a slow time. I want to finish quick. So I'm actually looking for a z-score that results in the bottom 20%. It also kind of goes with weight as well. If you want to be in the lowest or the top 20% or something, you have to pay attention to the scenario. So when I do INV norm, my area will be 0.2, and I'm going to get negative 0.84. So we have negative 0.84 equals x minus 58.6 all over 4.3. Multiply by 4.3. You get negative 3.612 equals x minus 58.6. Add 58.6. And we get 54.988 minutes. On the previous two examples we did, we were looking at scores, so I didn't need to really put units on them. But because we're looking at a problem containing time, I did need to make sure that my final answer contained the units that related to the problem, which were minutes. Okay. So our last example says an automobile dealer finds that the average price of a previously owned vehicle is $8,256. He decides to sell cars that will appeal to the middle 60% of the market in terms of price. Find the maximum and minimum prices of the cars the dealer will sell. The standard deviation is 1,150 and the variable is normally distributed. So if I'm looking for the middle 60%, that means I have 2 z-scores. Okay. It also means my remaining percent, which is 40%, is split up. So 20% is above and 20% is below. Now, we just did an example where we had where we were looking at 20%. So I know my 2 z-scores, negative 0.84 and positive 0.84. So I'm going to use both of these z-scores to solve for the minimum and maximum prices. So for the minimum price, negative 0.84 equals x minus 82.56 over 1150. I'm going to multiply by 1150. We'll get negative 966. And then add 82.56 and we'll get 72.90. For our maximum, we're going to use positive 0.84 equals x minus 82.56 over 1150. The only difference is when I multiply by 1150, I'll get a positive 966. So then 966 plus 82.56 is going to give us 9222. So he should sell cars between $7,290 and $9,222. Please let me know if you have any questions about the normal distribution, z-scores, using your calculator, or using the table.